So we could do the same process for any value less than 1, between -1 and 0, between 0 and 1, and greater than 1. So here are the recommended ones to try. But we could use, like it says, any values. So if I said that I had n where I have r to the power of n, then if I had -2 to the power of 1, it's going to be -2. To the power of 2 is going to be 4. To the power of 3 is going to be -8. To the power of 4 is going to be 16. To the power of 10 is going to be 1024. To the power of 20 is going to be 1,048,576. And when I do it to the power of 100, it's so big that I would have to say that it's going to be approximately 1.3 times 10 to the 30. If I pick a number between -1 and 0, in this case 1/4, then 1/4 to the power of 1 is just the original number. To the power of 2 is 1/16. To the power of 3 is -1/64. To the power of 4 is going to be 1/256. To the power of 10 is already getting so small that I have to write it as 9.5 times 10 to the -7. To the power of 20 is going to be 9.1 times 10 to the -13. And if I said it was to the power of 100, I get 6.2 times 10 to the -61, an insanely small number. For the next example, use 2/3. To the power of 1, 2/3 is 2/3. To the power of 2, it's 4/9. To the power of 3, it's 8/27. To the power of 4, it's going to be 16/81. To the power of 10, I get 0.173, yada, yada, yada. To the power of 20, I get 3.0 times 10 to the -4. And to the power of 100, I get 2.5 times 10 to the -18. Once again, an insanely small number. Last but not least, what if we did to the power of 3, or the number 3? To the power of 1 is 3, power of 2 it's 9, power of 3 27, power of 4 is 81, power of 10 it's 59,049, power of 20 it's 3.5 times 10 to the power of 9, and to the power of 100 it's 5.2 times 10 to the 47. As n gets larger and larger, the sequence is going to be convergent if the value approaches 0. So if I had -1/4 or I had +2/3, you can see that these numbers get so small, whether it's on the positive or negative side, that it is going to get incredibly close to 0. The numbers are going to be divergent, like in our example of -2 and 3, where they get further and further away from 0. Those two numbers wound up getting massive, so big that they're almost immeasurable. So, what are the rules? As long as my R value isn't exactly 0, any number in between -1 and +1 should have an infinite sum. Now, technically, if I had 0, it would have an infinite sum, but it would just always be 0. But if it is a decimal or a fraction that exists between -1 and +1, then we're going to call that convergent. And it is going to have an infinite sum. If it is smaller than -1 or larger than +1, it is divergent. And we can't actually solve it. Now, how can we solve this? Well, if I said that the sum is the first term plus the first term times the common ratio, and then the first term times the common ratio squared, and then common ratio cubed, and yada, 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 then we have our sum is going to be my first term times the common ratio to the power of n minus 1 over my common ratio minus 1. As long as r is in between -1 and 1, it's going to get closer to 0 as n gets closer and closer to infinity, which means that we can replace Rn by 0 in the formula. Because if I take r to the power of n and it's in between -1 and +1, then if my n value is infinity, my r value is 0, and 0 to the power of infinity is still just 0. This is going to eliminate this part of my equation, and then it's just going to be my first term times 1. So I can say that I take my first term times 1 and divide it by 1 minus my common ratio, and that is always going to wind up giving me what that infinite sum is. So we can have a finite series where we can solve for the actual value of the sum. We can have a infinite series where it is a common ratio between -1 and +1, and I can solve for what the infinite sum is. Or I can have it where it is greater than 1 or less than -1, and there is no calculable sum. It's going to get further and further and further apart, so I can't actually solve what that sum is unless I only have a finite number of terms. If this is true, then we should be able to actually solve this. It says determine the common ratio for each of the following geometric series and state whether a sum is going to exist. So in this case, my R value would be my second term divided by my first term, or 1/3, which means that it does have an infinite sum because that would be the same as 0.3 repeater. And then I can actually calculate the infinite sum. I'm going to take my first term, and I'm going to divide it by 1 minus my common ratio. And this is going to have an infinite sum of 1.5, or 3/2. For example B, I'm going to take 1, or the negative 5 divided by 1, and my R value is just negative 5. No infinite sum. For example C, I'm going to take negative 1 and divide it by 2, and I get negative 1 over 2. That is in between negative 1 and positive 1, so my infinite sum is going to equal my first term, 2, divided by 1 minus negative 1/2. I plug that all into my calculator, and I'm going to get an infinite sum of 4 over 3. Now, we already know we can rearrange formulas to solve for other pieces that are missing. So in this case, for example 2, it tells me the first term, it tells me the infinite sum, and it wants to know what my R value is. So if I use that formula that we've been using and say the infinite sum is equal to my first term divided by 1 minus R, and I'm going to sub in for my infinite sum, 4, then I'm going to multiply both sides by 1 minus R to move that out of the denominator. 4 times 1 minus R is equal to 2. I'm going to divide both sides by 4, or what my sum is, and get 1 over 2. I'm going to subtract 1 from each side, and then I'm going to flip the sign. We can use an infinite series to represent a repeating decimal. If I said that I had 0.077777, so on and so forth, then I could say that all I'm doing is I'm adding each digit that comes after the first 7. How would I write that? Well, I would say that I take my first term, 0.07, which is my first 7 that exists. I'm adding to it the next decimal place, so 0.007. I'm adding the next decimal place, 0.0007, and I'm going to keep doing that forever. Which means that my first term is 0.07. How do I get from one term to the next? Well, I'm moving the decimal place, which means that I'm dividing by 10 or multiplying by 0.1. And then I can write this as an infinite sum by saying that I have 0.07 divided by 1 minus 0.1. And when I put that in my calculator, that's going to be the same as 7 over 90. I can double check and put 7 over 90 in my calculator, and I'm going to get 0.077777 going on forever. And it makes sense.